second lecture. I will talk about the topology in unknown spaces. By the topology, I mean we talk about convergence of sequences basically. I'm not going to talk about open sets and so on. So, just some aspects of topology that are related to what we need in proving theorems like fixed point theorems. Completeness is important, and so before that we need to know the notion of convergence of sequence in unknown spaces. But before that, let me start with by repeating what I discussed yesterday, especially this one, just to give you a better geometric interpretation about two inner products and two norms. So yesterday I mentioned that this expression is really the cosine of the angle, and by that I mean it is really cosine of the angle. In the case of two standard inner product and two standard norm involving the inner product that we have in the space. So if X is an inner product space, then we are actually talking about geometric angle. How do we know that? Well, if this is the parallelogram spanned by X and Z, and that is the parallelogram spanned by Y and Z, how do we measure the angle? Well, from high school we know that we have to project this perpendicularly. We talked about orthogonal projection just now, and also this vector, perhaps to that. And so the angle is basically between these two vectors, right? These two vectors. But we have a complicated formula there. Is this really the cosine of these two vectors? If I call this vectors y prime and this is x prime, so x prime is the projection of x on z, and y prime is the projection. Complements. So x prime is x minus projection, right? And y prime is y minus the projection of y on z. So if we keep that in mind, then we do the elementary row operation by, for example, here I have x and then I have z there. So I can subtract the first, because this is just a multiple of z, right? This is just a multiple of z. Think of that as alpha times z. We don't really need the value of the alpha. So if we subtract the first row by alpha times z times the second row, then we get x prime. Okay? And here x prime also. And the second row is still the same. Okay, so the value of the determinant is unchanged when we do that. Okay? And we do the same with the denominator here. So this is x prime z, and the second row is the same. And we can also do that with y. So y is subtracted by I say beta times z, we don't need the value of beta, so we get y prime, y, and y prime z. Second row the same. Okay. Up to now, I think we can simplify the expression here, because now x prime in the inner product of x prime and z is 0, right? Okay, so this thing is 0, that thing is 0, that thing is also 0. So, okay. But we have to do one more operation. Now we do it with the column. You see y here and you see z there. We can also subtract beta times the second column from the first column, and so we get on top we get x prime, y prime, x prime, z, and then z, y prime, z, z, and at the bottom we get now we do the operation for x in the first column. We subtract alpha times the second column, so we get x prime, x prime, x prime, z, z, x prime, z, z, and also for y we subtract by a multiple of second column, so we get y prime z, and then z, y prime, z, z. Okay? Now we just compute, we see that on top we get x prime, y prime multiplied by the inner product of z with itself, but that is the norm of z squared, right? And you don't have to subtract by that because it's 0. Okay? So here we get norm of x prime squared times I missed something. I missed square. I missed a square, so I have to have square root there. But okay, so the square root. So taking the square root, I only have norm of x prime times norm of z, and here norm of y prime times norm of z. So the norm of z squared cancels. So that this is really the cosine between the cosine of the angle between x prime and y prime. So I just justified that what I said yesterday, that this expression is really the cosine of the angle between the parallelogram spanned by x and z and the parallelogram spanned by y and z. But this is of course in the standard case. But in general, we can interpret that expression as the cosine of the angle too, because we have Cauchy-Schwarz inequality. The value is, the absolute value of that expression is less than or equal to 1. So if we define it as the cosine of the angle, then yeah, it's okay. Okay, so that was something I want to add from lecture. Today we'll talk about the topology, and we want particularly to define the convergence of a sequence in an unknown space. So the way we define it is just like in this picture. Z is just like parameters. So we focus on one factor only, which may vary. Okay, so a sequence now, for not to be conflicted with the indices of the vector itself when x is also a sequence, I write the sequence like this. So x of k, basically a sequence is a function, right? So this notation is natural. So a sequence x of k in a known space, x with this unknown, is said to be convergent to a vector x in a space if and only if this limit is equal to 0 for all x2 up to xn in x. So here we treat, or we consider x2 up to xn like parameters, or like test factors. Okay, so what we are focusing is on the first vector x of k minus x. So if by subtracting x from x of k makes this goes to 0 as k goes to infinity, then we say that x of k convergent to x. Remember, the n norm is invariant under permutation, so actually you can also play with the other factor, but we choose, of course, the first factor to be in that commutation of the limit. So in such a case, we write that the limit of the sequence is equal to x and call x a limit. I haven't used the word "did" because we don't know the uniqueness, but soon we prove it that if it exists, then it is unique, and later on we can call it the limit of the sequence. How do we prove the uniqueness? Well, it's the same as we prove the uniqueness of the limit in known space, but now of course we have factors x2 up to xn that we have to choose carefully. By supposing that the sequence converges to two vectors, x and y, with x is different or distinct from y, so we assume that happens, then we can choose x2 up to xn such that this n norm is not 0. Why is that? If the vector is not 0, then in the space there are many other vectors. The dimension is at least n, so we can have other vectors so that we have n vectors who are linearly independent. So that the n norm by property 1 Is it property 1? Yes, property 1 is non-negative. Okay? It's positive. So we can choose then the epsilon to be a half of that, and by the convergence there should be k such that on one hand this is true, so this norm is less than epsilon, but on the other hand we also have that. Okay? But then by the triangle inequality of the n norm, we have this. And the sum of this is less than 2 epsilon. And 2 epsilon is equal to the norm of x minus y, x to xn up to xn. And here we have a contradiction. We have something positive less than but itself. So impossible. So the limit must be unique. Okay? That's what we would like to have with the limit of the sequence. So, although the previous definition of the convergence of a sequence works fine, we find that the condition requiring the limit must be 0 for all, I put the word all in italic, for all vectors x2 up to xn is rather too much. I use the phrase test vectors or testing vectors. So in my mind, I think of x2 up to xn just like testing vectors. So in this picture, z, but I can play around with z. What if I change the z to other vectors? Also here, what if I change x2 up to xn from one condition to another? Do I still have the limit equals to 0, something like that? But by saying all, I think it's too much. So the problem is how do we reduce the condition, right? In many mathematical notion, we want the condition to be precise, not too much, but also not less than necessary. Okay, so some researchers weaken the condition by requiring that the limit is 0 for some fixed vectors. So just fixed. So they are not parameters anymore. They are fixed. But then this is too loose. I use the phrase too loose. For instance, using this requirement, the sequence x of k that has term like this is converges to 0, because when you put x of k here, and you see here, there's always x2 pops in. So you put x2, the subsequence with odd terms, it will be 0, and here is fixed, right? N is fixed. Imagine n is 10. So for the even terms, you have always a multiple of xn. So if you put that here, you get also 0. So if the odd terms goes to 0, the even terms goes to 0 also, then this thing must go to 0. Okay? But I don't see that this is close to 0. Okay? So if we are to reduce too much, then we get something funny. So we don't want that too. Okay? So the problem is to find the sets of vectors x2 up to xn that we can use to define that the sequence is convergent to a limit, in the sense that if we draw it, for example, we want something convergent to x, so intuitively we want something that is really approaching x, okay, in common sense. But of course we don't know what the space is, so we have to make sure that we get the definition such that when x is an inner product, for example, inner product space, then that happens. I mean, the definition should coincide with the usual definition of convergence. So, whatever the definition, we will check with the noun situation, like in the product spaces or LP spaces and some other spaces that we already know. Okay. So we want to reduce the testing vectors such that when x is also equipped with a norm, the limit coincides with the limit in a norm, or if x is equipped with inner product, the same thing also happens. So at least when x is equipped with the norm, like in LP or some other spaces that we know. And this problem is solved in most cases. I will explain why I write in most cases, not in all cases, by choosing any linearly independent set A1 up to AN of n vectors in X, and requiring that the limit is 0 only for these vectors. How many are there? Well, there are n vectors here, so there are n numbers there, and here there are n minus 1 number. So it's n choose n minus 1, and you know that's only n combinations. Okay, so only n combinations. Take the first one out, plug in there. Take the second one out, plug in there. Take the third one out, plug in there. Up to take the last one out, plug in there. So that's it. So this is finite checking process that we can do. It would be nice if that is our definition. But the problem is, of course, originally, I don't know if it's Gahler or MYSAGA or someone, wrote that definition with all x2, x3 up to xm. So if I reduce the definition to this, of course I want to check whether this implies the original version. The original version, of course, will imply this because I use only n combinations, right? And possibilities here. But do I also can I also get the original definition from this very restricted condition? So in most cases, yes. Yeah? Okay, I've said this already, that instead of checking infinitely many limits, we only need to verify any limits only. So why I wrote in most cases? Because I want to make sure that can get the original definition of convergence, even though I only work with this finitely many set of vectors. Okay, I don't write in my slides in what cases that I got what I want. Okay, but if you check my publications with my former students like SC and who else, they're not here. You can see that in finite dimensional cases, for example, even the dimension is 100, for example, then I work with n only, n is 10, for example. I can get that the limit is 0 for all possible y or infinite dimensional, all nodes are equivalent, so I use that fact and use some other inequalities and so on. So, and also in inner product spaces, even the dimension is infinite, but if I have an inner product, then I also get the result by using Hadamard inequality and so on and so on. In LB spaces, that's what I will explain a little bit in my next slides. We can also get the result. Okay? And this afternoon, Harry will explain more about alternative approach. Maybe we don't need to use those, but need something else also. Okay, but now let's stick with the original idea is to use a set of n linearly independent vectors. I call them testing vectors. Now, you have to be a little bit imaginative. N is too many, perhaps, how about 3? Okay? We are working in 3 space. So this 3, you choose 2, you plug into the node. If it is 0, then the vector must be a linear combination of these 2. You choose another 2, must be a linear combination of those second choice of 2 vectors. And then if you choose the other 2, it must be 0. Then the vector must be 0. That's your conclusion. Okay? So, in general, we get this fact. So if A1 up to AN is a set of n linearly independent vectors, and if it is 0 for all n minus 1 possible vectors taken from n1 up to n, then x must be 0. And this fact is important when you prove the uniqueness, remember? So if x is not 0, then this must not be must not be equal to 0. Okay, so I talk about the what do you call that? The converse of this implication. So that's a nice fact about this condition being 0. Okay. Many results in normal spaces, such as fixed point theorems, I will prove one version of it on LP, have analogs in n-norm spaces. And originally, many years ago, when I think it's about the same time as you studied here, into the year 2000, this is when I started to learn the subject in the year 2000. I look at the papers. So many papers, many researchers prove, for example, fixed point theorems and many other results in n-norm space by imitating the proof in norm spaces. Yeah. By that I mean, for example, what do we do when we want to prove a fixed point theorem? We do it iteratively. We start with the point, then we apply the operator, we get the next point, and so on and so on. We get the sequence, and then yeah, finally we prove it convergence, and the limit is the fixed point that we are looking for, and then we prove the uniqueness. That's exactly what they do, except they now have an extra vectors they consider as parameters. So there are differences here when you use parameters. Maybe not so important, but I used testing factors. So I think, and I want to reduce the number of testing vectors. And then I don't want to imitate the proof of the proof of the fixed point theorem in norm spaces to the proof of fixed point theorem in n-norm spaces. I don't want to do that. It must be simpler. It has to be simpler. That's what I thought, and that's the case actually. Okay, but of course I will explain more in detail about that. So we found that we could obtain the same results differently by using a set of n linearly independent vectors, and then define a norm, like either define a norm from a semi and a product. Here I will define a norm from the n-norm. Yesterday I told you how to define an n-norm from a norm using Galer's, at least. Galer is one possibility, and in certain spaces like LP there are other formula, right? So a norm space is an n-norm space. Now an n-norm space is a norm space. Here is the formula for the norm. Again, I'm using the set of n linearly independent vectors. We can define this expression. P is, you can take P is equal to 1, but P is like in LP from 1 up to infinity. Of course, when P is equal to infinity, you consider this as the supremum. So we have many choices here depending on P, but I put P because later on I will also discuss LP. So, but you can think of P is equal to 1, for example. If P is equal to 1, then you just have the sum, and that is a norm. Okay, we already proved the fact that if it is 0, then x must be 0. Okay, so that is the first property of a norm. And then you can check the second property, the third property, and the triangle inequality, the last property. Exercise. Okay? And then give me an idea. That's exercise. Prove that it is a norm, or prove this fact. Okay? Okay. So P becomes index there, and I put a star because later on there is also norm in LP, so not to be conflicted with the LP norm, I put a star there. So you can check that it is a norm. Using this fact, we could prove fixed point theorems and many other results by exploiting our knowledge of norm spaces. So the difference with many other people who work on this subject is like this. We have a norm space here, we have an n-norm space there. I don't know if I can visualize this. We have a norm space, norm spaces, we have n norm spaces. We have a norm here, we have an n norm there. Okay? So here we have fixed point theorem, for example, with the proof. And here they also prove fixed point theorem with the proof. And this just imitates. They import the proof here to there. I don't want this. Okay? So what I do is, here we have norm spaces. We have n-norm spaces. Here we have an n-norm, and from here we define this norm. And I compare that with this norm. Okay? So instead of importing what we know from the norm spaces, what did I do it? Importing. Now I export this to this. Okay? Of course, it is not exactly the norm here, but if they are equivalent, then I got the result. That's the idea. Instead of importing, I'm exporting. Okay? It's good for the economy, right? So, don't just import, and import. Export. Well, maybe not exactly the same situation, but there is a difference between this approach and that approach. I will tell you, the proof is very short for the fixed point theorem. Once we do that, proof is very short. So, for example, this paper, Karyani was my doctoral student at that time. Idris was my doctoral student also. And Essie also did something. So, for example, this theorem, fixed point theorem on L. Okay? So, the statement reads like this. So, let T be a self-mapping of LP, which is contractive with respect to. Now, this phrase appears everywhere, especially in the paper, but here maybe just once or twice. With respect to this, meaning that the contractive condition holds for any n-1 factors coming from these factors. So actually we have how many inequalities? We have n inequalities. Not infinitely many, but we have n only. So if we have this, there is a constant c, so of course c doesn't have to be defined, because if there are n constants, we just choose the largest one. Sorry. Yeah, they are all in this interval. So c is in that interval. Then T must have a unique fixed point. Okay, how do we prove it? Remember that scheme. So, but of course we need some preparation for that. Okay, first is the one you asked yesterday. So this is the relation between the n norm, but this is not Galen norm. This is the norm that I defined. I don't want to call it my name. I don't know. And we have this extra vector. Even if p is equal to 2, this is not equal to 1. So this is a little bit worse than Hadamard inequality. Hadamard inequality for p equals to 2, the constant there is 1. So there is an opportunity to improve this inequality, but we don't need a sharp 1 here. This is sufficient for our purpose. And using this lemma, we can prove that the norm we define in fact 0.6 is equivalent to the usual norm. That is important. But to prove this is actually a bit cumbersome. You check our paper, a lot of computation. Actually, I didn't succeed in the first time to prove this. I needed to wait till I got a bright student, Idris, who helped me to play around with the expressions, and we got the proof. And then with that, LP equipped with this norm is also complete. Take a sequence, Cauchy sequence here. The Cauchy sequence will also be Cauchy sequence in LP with the original norm, and so this converges in LP with the original norm, but the limit should be also the limit in this norm. So it is a Bandung space. Now with this lemma, the proof of the fixed form theorem is just like this. You see? We just proved that T is contractive with this norm, and so we are done. We don't have to repeat all the iterative procedure and so on. That is the idea, and you can check the paper about this. There are many, and also Elsie has done some other theorems with some modifications. So, yeah, there are many fixed point theorems. Right? So, I guess I stop there. Any question? Yeah, non-expensive mapping. Did we discuss that? I don't remember if we have discussed that, but of course we can do similar ideas. Yeah, we export instead of import. Yes, once we export. So this is like exporting. Export the contractive condition to this. So the idea is like this. Yeah. But once we are successful, then we think that we are finished. So we work on something else. But I think exercise for my students. Non-expansive mapping, and there are many other variations, right, of fixed point. Okay. Yeah. When I explain this to my students, sometimes I use this diagram. I get the original hypothesis in n-norm spaces, and then I move to the norm that I define, and then I compare it to the norm that is there also. And then I go back here to the Hadaman type inequality. So I sometimes use this diagram to prove, like, for example, Cauchy property, completeness, and so on and so on. Okay. So in this second lecture, I have explained if we also have a norm, how we can work from the n norm to the norm, and if there are other norms already defined there, then we can compare. In finite dimensional case, of course, the two norms are always equivalent, so that was what I said. In finite dimensional case, it's finished. But in the infinite dimensional case, LP continuous functions, we have checked that this still works also, but we cannot conclude that we have covered all cases. So that's why I use in most cases. Maybe I'm too optimistic by using the word most. Maybe I should say in many cases. Very much.